Hello everyone. I am going to go over a worksheet here on with my document camera that will help you get ready for the test you have this week, and you're going to answer a couple questions in this Edpuzzle about it. All right, so I'm going to go pretty quickly so that it's not too long. Determine the domain of the functions algebraically. Check with your TI. Okay, so we've got to look out for restrictions before we can establish the domain, and we're going to be looking at even roots and denominators. Those are going to present a potential problem, and this is an even root, so I've got to ensure that what is underneath that even root is positive. We don't want any imaginary numbers, or 0 would be okay because the root of 0 is 0, so that's okay. So I'm going to take what's under the radical and set it greater than or equal to 0. So x is greater than or equal to -8, and you can just pop that to interval notation right there, but just visually to show it, since we're not going to check with the TI, I'll just do a rough little graph here. This is just all of these values this way, okay? And so in interval notation, that would be a bracket because it's inclusive. 0 is okay under the root, and we shoot left and right, or the domain is a left and right, so we're shooting right to positive infinity. Our next problem is an absolute value. I don't see a radical, I don't see a denominator, so I could instantly just jump to all real numbers here, but let's just graph it just to review transformations. This is absolute value. There's a V in the word value, so this graph will be a V. That's just a nice little way to remember the shape of the parent function. This is going to be left 5 and up 3 for the vertex. So 1, 2, 3, 4, 5, 1, 2, 3, and there's your V shape. That's -5, 3, that's a point right there. So looking at the domain, this arrow here means infinitely left, and this arrow here means infinitely right. So our interval would be, interval notation of our domain would be -infinity to infinity. Here we have a denominator. We have to ensure that it is not 0, and also have a root, an even root, and so we need to ensure that it's positive. So, with a root, we would say 3x plus 5 is greater than or equal to 0. However, since it's in the denominator, we can't use that or equal to, so we have to just set this greater than 0. All right, so x is greater than -5/3, and I think we're good to go with interval notation without a number line. Greater than, so non-inclusive, so there's our leftmost point, and this shoots off to positive infinity when we're thinking in an x perspective. Domain is defined with x, so we're thinking left, right. All right, piecewise. So we've got two rules here. The first rule is a parabola shifted up 7 for values x less than 1. So I'm going to do a little t-table here like we did in class. So I want to go 1. I want that to be open, and I'm going to go just a couple points there. I'll do 1, 0, and -1. So in they go. This function. 1 will give me 8, 0 will give me 7, and -1 squared will be 1 plus 7 is 8. So I see some symmetry there, which means I'm going to realize my minimum. So that's plenty of points. We know this will be a U-shaped. So let's go to 1, 8, 1, 2, 3, 4, 5, 6, 7, 8. I'm big on labeling, so we're going to label that point. And there's our 0, 7, and here's our -1, 8, and we've got the U shape established, and there you go. So there's the graph of the first rule. I'm going to go and answer these questions here too, because why not? I just did f of 0, and f of 0 when plugged into this domain of x is less than 1, that is going to be equal to 7, and we saw that -1 is equal to this 8, and I want to be careful here not to say that f of 1 is 8 because that is an open dot. So we put 1, 8 there. It's an open dot. It doesn't actually, it's not part of the graph. It's everything up to 1 coming in from the left, but it's open, so we don't want to give that function a value of 8 here. We want to move on to the second rule because that is where the rule changes that 1, and now for x values greater than or equal to 1, we are now going to be linear. All right, I'll change color since we're changing rules. Let's go to 1. And this is a line, so we only need 2 points to make a line. So if I had x in between two values here, I would use those two key values. But the only key value here I have is 1, so let's just see what that is. That's going to be, we're going to put our 1 in here, and we're going to get 1, 2. So we'll go ahead and answer that question. So at 1 we're at 2, and that is closed. Because of that, or equal to, this is closed because of this symbol here. And then 2 points make a line from geometry, so you could either use your slope of -3/1 to get here, or since I have to do f of 2, why not just let that be my second point? So f of 2 will be -3 times 2, which is -6 plus 5, which is -1. All right. Where am I here? Okay, so that was the point 2, -1. And this does not have a rightmost bound. This is just going infinitely right, so this will have the arrow here. Both of these will have the arrow here because x is not in between two numbers. Okay, moving on. We're going to graph this with our TI. I went ahead and put it on paper, just to save time here. Let me get this where we can see it. So here's the graph. And how would we do that in TI? We would turn it on and then put in our 3x minus x cubed. I'm going to zoom 6 this, so it's on a standard, zoom 6, and then graph. There's the graph so you can see what I have there. So we're asked to find the local. All right, this is local because you have these arrows. We're not on a closed interval, so any max and mins here will be local. They'll be in the neighborhood. They'll just be where we change from decreasing to increasing or increasing to decreasing. So on the TI, I'm going to find that minimum first. So now I just went to second trace there, second trace, and I'm going to select 3. That's your minimum. And then we're going to go a little bit to the left, hit enter. I'm just hitting enter. You can't see my hand down there because it's too zoomed in, and a little bit to the right, and then I'm going to back it up here and just guess, and it's going to give me this lovely minimum value of -1, -2. So let's label that on the graph, and let's head on to second trace. I just hit second trace right there, and now I want to do the maximum, which is option 4, and we'll cruise over with I'm moving left, right, so I'm moving my left arrow a little bit to the left, enter, a little bit to the right, enter, back it up, and guess, and we get our max is equal to, and we're going to go ahead and put that as a 1. That's your TI's version of 1. It's quirky like that with certain situations, so you're not going to do at 9 repeating. You're going to go 1, 2. All right, so the local maximum, remember this is a value. This is a y value, so that is 2. Don't give the point. The maximum is the value. The x is where it occurs. And then, so there's that. And the local minimum then is the -2. Okay, so now let's answer these questions here. The intervals for which f of x is increasing, decreasing, CCU, and CCD. All right, so let's just take a walk, and we're on the decrease until we hit this point right here. Remember, this is where it's happening, so we're going to focus on our x values. Focus on any and all x values here because this is where it's happening. And so we are on the decrease. This up here reads, if you were to, this is left and up. If you were to make it a point, which really isn't a thing, but it's helpful when you're writing an interval notation, this is right and down. And so we want to focus on these x values. So we are on the decrease. We'll go here from -infinity until we hit this minimum, this relative minimum, this local minimum of -1. All right, and then we're on the increase, so we're going to go from -1 to 1. That x value is the focus here, and then I'm going to do a union symbol because MathXL does, and then this is 1, and then on to the right, infinitely right. Okay. So there we go. We're going to use parentheses there. You're welcome to use brackets. You're welcome to use brackets here if you're loyal to pre-calculus. If you're loyal to calculus, you're going to use your parentheses. This has to be a parentheses, and this has to be a parentheses because you cannot enclose infinity, but I would accept a bracket here or a parentheses, your choice. Now, concave up, it has to be a parentheses, so, I always say, why not always just go with the parentheses. And so we got to split the difference here between the local min and the local max. We're just going to, this would be concave up, and this would be concave down. So we've got this shared space space here. And so I'm going to split the difference between that shared space. And if we just did the midpoint between -1 and 1, that would be 0 divided by 2. And negative, we've got some nice symmetry here. -2 plus 2 divided by 2. So that would be 0, 0 on a midpoint. And so we're going to call that our POI, which stands for point of inflection. So we are CCU focusing on the x values. So that negative infinity, that's infinitely left. And we're going to be CCU until we hit the 0. And then we're going to be CCD picking up at that 0 and all the way right. Okay, so concave up would hold water, or it looks like a cup. Concave down water would spill out, or concave down looks like a frown. All right, next page, and we're going to cut some of this out because it's not on the test. So, sorry, I don't see names there. We're going to not do all of this. The difference quotient. Okay, so part 1, part 2, and part 3, we want to analyze f of x plus h. So x plus h quantity squared plus 3 times x plus h minus 2. There's part 1 where you plug in the x plus h through the whole function. Now we're going to subtract the function off itself. So you want to engage a parenthesis there. All right, and then that way you won't miss your signs, and then h is just h. That's part 3. That's the easiest part, just h. We're going to expand our binomial correctly, not forgetting our middle sign, and distribute. Not going to forget about this -2 here. Don't forget about this. There's no plug-in, but it is still there. And then minus off all of these guys, so their signs will all change. And we are going to hope that we get lots of cancellations because that is the nature of the difference quotient, and we indeed do. So we are left with 2xh plus h squared plus 3h. And what do we always want to do in a situation like this? We want to see if we can factor and cancel, and we can factor out an h. And when we factor out an h, we are able to arrive at the simplest form of our difference quotient, which is this. Okay, algebraically determine if the relation is a function. So we want to make sure that every input, every x is paired with exactly one output. So what we want to do algebraically to do this is we want to solve it for y. I mean, honestly, you can just look at it, and if you see an even power, like we said in class, on y, you're going to have an issue. But since we have to show it, you're going to want to solve for y to algebraically show this. So negative y squared equals 25 minus x squared. Y squared equals, I'm going to switch these signs, so I'm just going to do a little flip there. Y equals, we're using the square root theorem right now, so when you take the square root of both sides, in comes the plus and minus, and x squared minus 25. So this is going to be an issue. So if we plugged in a number, say, if you plugged in some number here, whatever you plug in, once it gets squared and then you subtract 25 from it, you're going to get some result, and then this plus and minus piece is going to give you two y's for the same x, and that's an issue. If I just, if I just let x equal to, say, 6, if we let x equal to 6 in this problem, we would get y equals plus or minus 36 minus 25, and so y is equaling plus or minus root 11, and so points here would be 6 root 11 and 6 negative root 11, and this is not a function. Okay, not a function. You can't have 6 branch out. You can't have a 95 be an A and a 95 be an, a C. So this is not a function. No, and what's your language? Each input does not pair, however you say it, does not pair with exactly one output. Okay, so this we are going to scratch because it's not on the test, and determine the interval for which this is increasing. This is really easy. This is good to bring up because it brings in some 2.5. This is a parent function of a parabola that is shifted right 3 and up 2. So 1, 2, 3, 1, 2. graph it. 3, 2. So where are we increasing? It starts at that minimum onto the increase. And so we are increasing, starting at 3, using your x values because you're telling where this happens. I'm loyal to calculus, so I use parentheses. And then on to this infinitely right behavior. Okay, there is your, there is that. That one's pretty easy. And then determine whether a function is even, odd, or neither. Show correct function notation. So what do we do here? We plug in a negative x and we analyze the result. So what I wrote right there is saying I'm plugging in a negative x. So a negative x, quantity cubed minus 1, and then 3 minus negative x, quantity cubed. All right, I'm going to move over here because I'm running out of room. So f of negative x here, that's going to be negative x cubed minus 1, and that's going to be 3 plus x cubed. Okay, so with a fraction, we want to basically get all the signs in the numerator to change or all the signs in the denominator to change, because ultimately that would make a fraction negative. You don't want, you know, everything to change here and everything to change here, because that would be a negative over a negative, which is a positive. So I know that's really confusing sounding, but this isn't even going to run into anything that's all that confusing. The only signs that changed were this and this, and so there's no way that that's an exact match to make it even, and there's no way that it's a pure opposite of here. If I factored out a negative just to take a look, if I got a negative out of the top, I'd get x cubed plus 1, and if I brought a negative out of the bottom, I would get negative 3 minus x cubed, and you know, if those would cancel, and this is still not a pure opposite or the exact same thing. It's just you got nothing going on here. So this is neither, and how are we going to show that? Formally, we're going to say f of negative x did not equal, you know, basically no change there. It did not equal the function itself, and f of negative x did not equal the opposite of the function, and we would say therefore neither. All right, hope this helps, and happy studying for your test. Bye.